Hi there, I'm Luciana, and I'm excited to introduce our next speaker, Karen Jacks. Karen has been a database administrator for over 20 years and is now a senior solutions architect at Crunchy Data. Today, she'll be sharing insights on how you can optimize your database for analytics without compromising performance of your applications. I'm sure you'll find this very interesting. Please join me in welcoming Karen Jacks.
Hi, I'm Karen Jex. I'm a senior solutions architect at Crunchy Data, and I'm really happy to be taking part in PyLadies Con talking about how to optimize your database for analytics. This is me. I was a DBA for about 20 years before I became a senior database consultant and now a senior solutions architect, still working exclusively with databases. I've worked with a lot of developers along the way, and I've learned a lot from them. And I like to try to share what I know about databases in return. As in almost all of my talks, I use Postgres for the details and the examples in this talk, but the concepts are relevant to other database management systems. What am I actually going to talk about and why? Let's do a quick recap of different types of database activity to try to answer that question. You probably have at least one application with a database backend that's constantly being queried, inserted into, and updated by a number of application users. It could be a traditional payroll app or a banking app system, an online commerce site, or any other type of application. We usually call this type of workload OLTP, online transaction processing, or operational database activity. And it's characterized by many concurrent users performing short queries, often multiple selects, inserts, and update statements per transaction. Most applications constantly generate data from this OLTP activity, which gradually builds up in your database. And this data has immense value to the business. So at some point, the business wants to glean insights from that data. And for that, you need to run analytics queries. Analytics activity can take various forms, and it has lots of different names, such as OLAP, Online Analytical Processing, Reporting, Decision Support, DS, or Business Intelligence, BI. But it's basically any activity that's designed to answer real-world business questions. It might be how successful was our last marketing campaign, or what impact on our carbon emissions would action A have compared to action B? And these OLAP activities typically involve complex queries, often joining data from multiple tables, working on large data sets, and therefore often have very high resource utilization, whether that's CPU, memory, or I/O. So once upon a time, there were OLTP databases and there were OLAP databases, and the two were very much separate. Data would somehow be extracted from the various OLTP databases and loaded into the OLAP system, often via a nightly or weekly batch process. And this does sometimes still happen, and there are good reasons for doing it that way in certain cases. But often businesses want to get value from data where it is in real time. So they want to get the business intelligence directly from the OLTP system. Where you've got both OLTP and OLAP activity in the same database, you'll often hear it described as a mixed or hybrid workload. So what's the problem with this? Well, the chances are that your database is optimized for your day-to-day OLTP application activity. Adding analytics activity into the mix means you can end up with the worst of both worlds: inefficient analytics queries that also slow down your existing application. So now that we've identified the problem that we want to solve, let's set up an environment to test things out as we start to look at ways that we could fix the issues. Since coffee and cake are some of my favorite things, I used the coffee shop sales dataset that I found on Kaggle here to populate a coffee shop sales table. I expanded the data until I had 26.5 million rows in the table, just so that I had a decent amount of data to be working with. Then I created an analytics query to answer the slightly convoluted question, which store had the highest total sales for each month of the previous calendar year, taking into account only transactions with a value greater than 20. And this is the full query that I wrote to answer that question. The details of the query really aren't important. It's just important to know that it concatenates, filters, and aggregates data from that coffee shop sales table. And it creates output, a report that looks like this: 1 row per month, showing month, store, and total monthly sales. Let's have a look at the execution plan for the query so we can see what it's doing behind the scenes when it's run. To do that, I'm using the explain command, explain analyze in this case. So I simply typed explain analyze before my query. The analyze keyword is optional, but it tells Postgres to actually run the query so we get the real statistics rather than an estimation. And this is the execution plan that I got back from that. You don't need to read all of this and you don't need to understand what it's doing. It's just to show the kind of information you might get back. And I've pulled out the key details from this on the next slide. So amongst other things, we can see a full table scan on the coffee shop sales table. So we see there seek scan on coffee shop sales. That means it's reading through the whole of the coffee shop sales table. We can also see that it's doing some sorts on disk. We see sort method external merge and then disk with an amount of space. And we can see that it's taking just under 3 seconds to execute. So we've got our environment in place. Let's have a look at some of the different techniques you can use to optimize your analytics activity without slowing down your application. It's not going to be an exhaustive list. The idea is to give you just enough to get you started. Your database configuration parameters have probably, hopefully at least, been set to optimize your day-to-day database activity. If not, then I recommend going off and having a look at them before you do anything else. Which gives me the excuse for a shameless plug. I've included a link to a talk I gave on that subject in 2023. For any parameter that has to be set across the entire instance, you'll need to find a compromise that works best for your hybrid workload. Some parameters, though, can be set for specific users, so you can set them to different values for your application users and your analytics users. Some can even be set for individual statements. We'll have a look at just a few parameters. The max connections parameter specifies the maximum number of concurrent client connections that are allowed for your entire Postgres instance. It's 100 by default, and on most systems, you don't want to increase it too much higher than that. The chances are there won't be that many concurrent analytics connections, but those connections, as we said earlier, are likely to be using a lot of resources. So you probably want to restrict those to a much smaller number. And one way you can do that is by using connection pooling. You could create a separate, smaller pool of connections for your analytics connections. WorkMem is the maximum amount of memory that can be used by a query operation before it has to work on disk by creating a temporary file. By default, it's 4 megabytes, but complex queries that perform large sort or hash operations can benefit from a larger value. You can check if WorkMem needs to be increased by watching out for creation of temporary files. If you use log temp files and set that to 0, for example, you will see all log files that are created written into your Postgres logs. Just be careful because a complex query could run multiple sort or hash operations in parallel, and you might have several sessions doing that kind of thing in parallel. So you could end up using a lot of memory if you set this to a high value. To avoid that, you probably want to set WorkMem to a high value just for the specific analytics sessions that need it and limit the number of those. If you're worried that certain queries might run for too long, you can set statement timeout, which will abort any statements that run for longer than the specified amount of time. By default, it's set to 0, which means it's disabled. And although you can set statement timeout for the whole instance, it's probably better to set it just for specific sessions. You could set it to an appropriate value for different types of session. You could allow analytics queries, for example, to run for many minutes, but you might expect most of your application statements to take mere milliseconds. If you want to make sure that any statement that times out's logged in your PG logs, you need logmin error statement to be set to error or lower. You can see the valid values here from least severe, debug 5, through to the most severe, panic. So if it's set to error, any statements that cause errors, logs, fatal errors, or panics will be logged in your Postgres logs. You'll probably need to create specific indexes for your analytics queries. Just be aware, of course, that indexes need to be maintained. So if you create too many indexes on your application tables, not only will you use a lot of space for those, but you could also start slowing down your inserts and updates. As well as creating indexes on one or more table columns, you can also create indexes on functions or scalar expressions computed from your table columns. Here I created an index on the total sale amount expression that's used in our query. And then when I reran the query, I could see bitmap index scan on CSS total sale amount. So that shows that the index is being used. And in this case, the execution time went down to just over a second. Most analytics queries aggregate, sort, and calculate large amounts of data. We've got totals, averages, comparisons, groupings, etc. And these are resource-intensive operations, so it can be useful to pre-calculate or pre-sort some of the data to make the queries less expensive at query time. You can create a generated column whose values calculated automatically to match an expression used in your queries. So, for example, we might want a total sale amount column in the coffee shops table using that expression that we just looked at. You can do that by using the generated always as keyword when you add the column. And the stored keyword here says that it should be physically stored in the table rather than just calculated at query time. And you can also create indexes on those generated columns. This can improve query performance, but it will, of course, impact inserts into the table because that needs to be calculated. Now, we can use that calculated column total sale amount in our query instead of the original long expression that was calculated each time. A materialized view is a physical copy of the results of a query that can be queried like a normal table. Material views are a useful tool for pre-aggregating data, and they're particularly useful if you don't need completely up-to-date information. You can refresh them at the required interval to keep the reporting data fresh enough for your purposes. And again, you can create indexes on materialized views. So here I've created a materialized view on the ranked sales section of that original analytics query. And now wherever that block would have been used as part of a bigger query, so here, for example, in our original analytics query, you can now select from the materialized view instead, where the data's already been calculated, aggregated, and sorted. In this case, the analytics query completes in a couple of milliseconds instead of several seconds when it's selected, when it's selecting from the base tables. Of course, the best way to avoid impacting your application database is probably by not running analytics against its store. Even if you don't have a completely separate analytics environment, there are still some options that might be available to you. Most database environments already have a high availability architecture in place. That usually means that you have one or more standby databases that are kept in sync with the primary via physical replication. Those replica databases are available for read-only transactions, so you could send your analytics workload to one of those to take load off your primary application database. Just be aware that physical replication gives you an exact copy of your primary database instance, so you can't do things like create separate analytics users, create indexes, change the layout of the schema application, change the layout of your schema on the standby database. If you need changes, you'd have to make those on your primary database and let them be replicated over. Another option is logical replication. You can use this to replicate just certain schemas or certain tables from a publisher database, your application database, to a subscriber database, your analytics database. It's more complicated to set up and maintain than physical replication, but it does give you a lot more flexibility. You can replicate just a selection of objects. You can replicate to and from multiple targets and sources. Your subscriber database can be available for read-write operations, so you can create indexes, users, materialized views, etc., just on the subscriber database. So, in summary, we looked at various techniques to make sure your database is optimized for analytics activity with as little impact as possible on your application. First, if you can, use a physical or logical replica. So you've got a separate database for your analytics workload. Tune your configuration parameters for your hybrid workload. Consider carefully your indexing strategy. Create generated columns or materialized views to pre-aggregate, pre-sort, and pre-calculate data. And don't forget that you can combine these various techniques to get the results that you need. Thank you so much for listening, and I'll be really happy to answer any questions you have.
Thank you so much, Karen, for sharing your knowledge and experience with us. For those who may have any questions to Karen, I encourage you to leave a message at the PyLadiesCon channel in Discord.